the wave should be something like this. Maybe 1 plus something, maybe Vp of r. And this part represents the scattered wave. So this is the total wave function, a scalar wave function for the case when you don't have a scatterer, you don't have a periodic scatterer. Okay. And I can call this a psi of k and r. For the case when you have a periodic scatterer, you can say that that thing should look something like that. But then with the property that this has to be a periodic function of r, in the sense that if I were to write this as this, up of r, it must be true that up of r plus the lattice vector must be the same as up of r. Okay? Because I know that if this had been a solution, to that problem over here, if I translate my coordinate system by just some lattice constant, okay, that also should be the solution. So if I were to translate this thing, r plus rl, I should get e to the I k dot rl for the first term plus e to the I k dot r up of r. Okay. My solution should not change except for this phase factor, because in this coordinate system, the incident wave has been replaced by one that has been shifted by this amount of phase in this coordinate system that is new. So my solution should have this property that this thing has to be periodic according to the crystal lattice. Okay. So this is known as a Bloch-Floquet theorem, and this is known as a Bloch-Floquet wave, the wave that is consisting of a plane wave in the background plus a periodic wave. This is called a Bloch-Floquet wave. Okay, are there any questions so far? So in the case of the electronic crystal lattice, you will solve Schrödinger equation in a periodic potential. In the case of a photonic crystal, you will solve Maxwell's equations in a periodic lattice or periodic crystal lattice. Okay? And let's see how we do that. But first of all, let's think about a generalized Fourier series. And let's talk about what a reciprocal lattice vector is. Okay. We have the concept of a lattice vector, which is this lattice vector over here. And this Bloch-Floquet wave has to be accompanied by this periodic function so that it satisfies this criterion for periodicity. And it turns out that if you have such a function that is periodic, you can expand it in terms of a generalized Fourier series in this manner. Let me call this Uag, okay, e to the I g dot r, where this function has a property that if I were to add a lattice vector to it, it becomes itself. Okay, so there must be a constraint on this thing. This G is a summation of all reciprocal lattice vectors. And let's see what this reciprocal lattice vector is. So it must be that this vector G, which is called a reciprocal lattice vector, has a property that this product here should be just 1 and remain unchanged if this property is to be satisfied. So we find collections of G that will make this always 1. What are those G's then? Those G's are called the reciprocal lattice vectors, and they can be found quite easily if you know what these vectors are. If you know the original lattice vector A1, A2, and A3, you can find G, and I can just write down the solution without proof, and you can convince yourself that they, in fact, are the solution for the reciprocal lattice vectors. And you can show that if I define my reciprocal lattice vector G to be equal to L1 B1 plus L2 B2 plus L3 B3, where L1, L2, and L3 are integers. Okay, L1, L2, L3 integers. Okay, then what you need to show is that this is true. This is equal to 1. Okay, and you can easily show that if I pick my B1 to be equal to A1 cross A2 or A2 cross A3 times A1 dot A2 cross A3 times 2 pi, you can see that this must be orthogonal to A2 and A3. It's not orthogonal to A1, but it'll be orthogonal to A2 and A3. So when you multiply this thing out, it will have terms that consist of, if I multiply G dot R out, it will consist of things like integers times 6, B1 dot A1 plus N B2 dot A2 plus N P B3 dot A3 plus cross terms. Okay, my RL is this 3 terms over here. My G is this 3 terms over there. If I multiply them out, I should have what, 6 terms, right? This will be the self term plus the cross terms. If I define my B1 to be such that is of this form, the cross terms will vanish. You can easily see that A1 dot, A2 dot B1 equal to 0, A3 dot B1 equal to 0. But A1 dot B1 is not equal to 0 if I design my B1 to be such. But if I dot this with A1, this numerator and denominator cancel each other, and A1, B1 is just 2 pi. 2 pi times an integer. Because it's 2 pi times an integer, it contributes to a factor of 1 here. And similarly, I can design my B2. Okay, you know how to design your B2 now. You must be A1 cross A3 over A1 dot A2 cross A3 times 2 pi. And then this B2 would also have the property that the cross terms would vanish. Okay, but B2 times dotted with A2 And then if you use the simple vector identity numerator, cancel each other, and it will contribute to a phase of 2 pi as well. And then you can also write this one. This will be A1 cross A2, and then A1 dot A2 cross A3 times 2 pi. So if you design your A1, B1, B2, and B3 to be these 3 vectors, all the cross terms will vanish. All the self terms will just contribute to a factor of 2 times. And then if you plug it back in here, it gives you a factor of 1. Okay? And can you see that? Let me convince you of the middle term. That if I multiply by B2, or A2, B2 dot A2 is equal to A2 dot A1 cross A3 divided by this A1 dot A2 cross A3 times 2 pi. And then I know that this is equal to, if I use the identity for the numerator, I can write it as A1 dot A3 cross A2, right? So there's a minus sign there if I swap it around, but then it's minus 2 pi. It still works, okay? So this group of reciprocal lattice vectors work. It will always keep this to be a periodic function. If I sum over all g's, when I sum over all g's, it means I sum over all L1, L2, and L3. So this is called a generalized Fourier series expansion. It expands the periodic function in the Fourier space in a periodic manner that satisfies the block blockade theorem. Okay? Are there any questions regarding this? And there's another thing that you might find very interesting, which is that if I were to start with this block blockade wave, and if I were to change the k vector by a reciprocal lattice vector, I just add g to it and look at this block blockade function. What it does is that it only changes value over here. So I would have something like e to the I k dot r, e to the I g dot r u p of r. It will just change something like this, which means that this is also a periodic function, so I can rewrite this ut tilde of r. So if I change this wave function by a lattice vector g, it still remains to be a block blockade wave. Okay? It actually hasn't changed the solution, which means that after you have found the solution with this k vector, if you shift your k vector by g, okay, it should also satisfy the same equation or the same solution, because it's still the block blockade wave that you're talking about. So the solution that you have obtained is periodic in the coordinate space. The solution that you have obtained is also periodic in the Fourier space. In the Fourier space, represented by the k vector. Those are called the Brillouin zones. Okay, give rise to zones that repeat themselves in the Fourier space. Those things are called the Brillouin zone. Okay, so it's French, so you don't pronounce the L. I think the French never pronounce the L. They pronounce it as E. Brillouin zone. Brillouin zone, but we call it Brillouin zone. Okay, the I pronounces A. Uiuc. Okay, Brillouin zone. Okay. So those are called the Brillouin zones. And let's take a coffee break, and then we can come back and talk about this photonic crystals more.